There's always something. Okay, now we're going to get into some examples of working at the moment around an axis. This is a previous solution, as is most of the problems I work. You can access that on Canvas. And I think I'm going to start putting up the additions because I'm realizing that sometimes it's 141 of 6th edition and 141 of the 7th edition, and they're different. So I'll try and put that up. And we are to find in this problem the moment around the x-axis. Well, I'll draw the figure in a second. Because of tension, and then because of the weight. And I could not get this figure because yesterday I was like, oh, I'll just pull it in the morning, and I couldn't log in. So I'll have to explain it to you very, hopefully, detail. So this is the x-axis, and you have a hinge. Actually, I think the hinge goes all the way across. And a plate. But it's not perfectly flat. So in our y, there's an angle here. So it's a little bit fallen down. And then we have a z direction. Exactly in the middle of the plate, there is a weight going down, and that's what's causing it to fall. But before it can fall all the way, you have a tension in a cable that's holding it up.
Dr. Oldfather, is this it right here?
Yeah, that's exactly it.
Okay, I just found it on my Chegg textbook solution so I could see it.
Can you share that picture through the chat?
Yeah, I'll see if I can.
And if not, don't worry about it, but that'd be convenient. And I'll put when I upload it, I'll put the picture next to it. But yeah, that's exactly it. And this is point B, and this is point A. This is a distance on the wall. It is in the XZ plane, which is convenient. And this is O. And with tension, or with a cable, it's always in tension. It's never in compression. So we know that it is going to be positive going this way and positive going that way. You have a question in your homework that's about tension, and it says which way is the tension from this point and which way is the tension from that point. Well, in magnitude, they're equal to each other, but they just change direction in their sign. And remember that tension is always pulling from that point, so it's going to be away. If it was compression, say there was, you have like a concrete brick, then it would be going down. We'll get into compression when we get to trusses. I'm skipping way far ahead. So because this plate is down, point A is in 3 dimensions, it's farther down. So I hope my drawing is good enough for you to understand a little bit of what's going on there. And we are given that the tension is 143.4 newtons. And I'm going to skip some of the steps because I just hope that you know how to find a unit vector. But if you are still having some issues doing that, you can find the detailed solution online. But I want to focus on the new concepts rather than what we've been doing before. So the unit vector for A with respect to B is the exact opposite of the unit vector of B with respect to A. So if you find the unit vector going this way, you can easily convert it to the other way if you realize that you want to do a different point. However, I am going to choose to take my moment about B, because remember, we're looking for the moment caused by the tension about this axis. So we could look at the moment of B and then change it to the axis, or we can look at the moment of A and then change it to the axis. So we need an intermediate moment. And in your homework, I'm pretty sure, I don't want to say for sure, but I'm pretty sure it tells you what moment to take the moment about. But here it's not quite as straightforward. However, anytime you can work in 2 dimensions rather than 3 dimensions, you should always try and do that. This A has a Z component, it has a Y component, and it has an X component. However, this B just has an X component and it just has a Z component. If you don't see that and choose A rather than B, that's fine. It's just going to take a little extra step. So we want this force, and that is going to be NA with respect to B. And to do that, we first have to solve for RA with respect to B, because remember, we go from R to a unit vector, and then we convert to, in this case, it's going to be tension. So we have to find that unit vector as an intermediate step. And to do that, we have to get dr. And then we have NA with respect to B equals RA with respect to B over the magnitude of RA with respect to B. And in the solution online, it goes through this in detail, but I am not going to do that. I'm just going to give us the components of A with respect to B. So that is negative 449 in the I direction, negative 0.542 in the J direction, plus a 0.316 in the K direction. So you can solve for that with RAB over the magnitude of RAB. And don't forget, if you're using this in Wolfram Alpha or MATLAB or whatever have you, the function for this is norm. That way you don't have to type in all the square root of the sum of squares. It'll save you some simple errors that you get when you type that out a lot. Okay, so now we have our force at B. And we still need an R. And our R is going to be BO in the X direction and BO in the Y direction. RBO is 0.35 I plus 0.4 K, and this is given in the problem. It gives you all the coordinates of that, so all you have to do is plug that in pretty easily. So the moment at O, because of the force at B, will equal R cross F, and that R is BO cross F, or in this case, tension. And we're looking at the tension of A with respect to B. And we solve for this force by multiplying that magnitude times the unit vector of A with respect to B. And this was that 143.4 kilonewtons force. That's great. And then let us finish solving for this axis. MOX, and this is going to be a scalar, which is the magnitude. we'll take MOB dot with the unit vector in the x direction, which is easy because that is what we're defining everything by. And that is also, we can plug that in, cross PAB dot with x. And what you can also call that as, because we know it's in the positive direction, is we can get the vector form of that by multiplying it by the unit vector. So you're taking away the direction and then you're adding the direction back. So that's taking away the direction and then you're bringing it back by multiplying the unit vector back. And this you do a lot subconsciously in your head. So anytime you multiply something by cosine theta to get it in the I direction, you're essentially taking the cross product, getting the magnitude, and then multiplying it by it again to get the direction. I'm gonna write it in one line here. And don't forget that we got this from t times the unit vector of a with respect to b, and we got n a with respect to b with r a with respect to b over the magnitude of r a with respect to b. So mathematically, there's a lot of steps here, and in the solution online, you'll find that a lot of this problem is looking for this unit vector. Some of the problem is looking for this unit vector. And then the last portion, which isn't tons of mathematical work, is looking for the moment about the axis. But you'll need to remember that the r cross t ends up being a vector. And even though we usually think of it as like this arrow, in 3 dimensions, it's actually just a vector because it's defined by this positive vector by a positive moment. It's defined going around it, but it's that sum part. So when you use the right-hand rule, it's whatever direction that sum is facing, and you can get the components from your sum to an axis. So if we plug in the values, you'll find that MOX is 31.1 Newton meters about the x-axis. But we still have to find the moment due to the weight of this plate. We found the moment due to the tension, but now we need the moment due to the weight. And in the solutions online, he goes through this whole process again to find the moment of weight. So instead of using T, he uses W, and instead of using RBO, he uses the R that's to that point in the middle of the plate. However, you can also work it so that if you have Y in this direction, Z in this direction, so their X is coming out of the plate, we see that the moment to the tension that we just calculated is 31.1 newtons, which is in the X direction, so pivoting around that axis. We know that this is a static system. Acceleration is equal to 0. And because of that, we know that the moment is equal to 0, the sum of all of the moments. The only other moment that we have in this problem is the moment due to the weight. There's no torque around here because this is frictionless. So if you were to think about it, having the moment due to the tension has to be exactly negative of the moment due to weight. And for that reason, we know that the moment due to weight is also 31.1, but it's in the negative direction. It's in the negative direction because it's actually pulling the plate down. So you can go back through and do complicated work again. And if you're still having some like issues conceptualizing this, you can go back and look at that. Or you can just think about it as there's only one other moment in the problem, so it has to be exactly opposite. Does anyone have questions on that problem? Hopefully it's straightforward, but there's a lot of little steps. So if you get lost anywhere on the way, it's kind of chaos. That is all the example problems that I'm going to work today, but I want to talk a little bit about one of the homework questions that you're going to have. Not like individually, but just kind of conceptually all over the place. So there's a beam with one force. So these are three-dimensional forces. I can't remember what they're labeled, but they're three-dimensional forces, and you're looking at a point in the middle. It asks for the resultant force and the couple that's along with it. Because if you were to get rid of force 1 and force 2 and replace that with some resultant vector here, that's great, but you lose what's going on with the moment, because there is a distance here that is r2, and there is a distance here that is r1. So there is going to be some kind of moment in the middle of these, unless the force of 1 and the force of 2 add exactly opposite moments. In the problem we just worked, the tension was holding the plate up, not pulling the plate up, just holding it still. So we had one moment going down and one moment going up. But in this problem, especially based on how the question's worded, saying find the couple, we know that the moment from force 1 and the moment from force 2 are not exactly opposite. So this in the middle is not frictionless. There's something going on there that's holding this in place, because we are still assuming that acceleration equals 0. So it's going to end up having some kind of couple inside there. And in order to find that couple, you'll take the moment from this side and the moment of this side, and then find the difference. And that difference is going to be the moment that's left over. So when you get to the homework question and it says find the resultant in the couple, it's just the difference of those two moments, and calculating those in space, R1 cross F1, R2 cross F2. And you can use that equation that I gave earlier, or you can use Wolfram alpha, however you want to do that. Hopefully that gives you a little bit of guide on there. Does anyone have any other questions? I'm going to go ahead and wrap up. If not, that was everything that I had for today. And then, as always, if you have questions on the previous homework, I can work it in class. It's good if you give me a heads up, because then I can like really think about working the problem. But if you think about it afterwards, I can always make a short video and just post it as a quick explanation. Since office hours are kind of odd, I mean, yes, we can have a meeting, but sometimes it's just nice to just shoot a quick email and say, hey, can you work this? And then I work a little video. That may help. And then you can always replay it, which is nice. But if no one has any questions, I'm going to go ahead and wrap up and post these for anyone who missed this lecture. All right.